Hello everyone, my name is Akio Kasuga. Today I'm going to talk about a challenge concrete structures for the low carbon society. So I show you on a little bit history of our R&D and also some example of the low carbon technologies. So at the beginning, so everybody knows that the Roman concrete pantheon is more than 2,000 years old. But our recent modern technologies, reinforced concrete, process concrete, that is more than 100 years, but now we have a very, very severe problem like deterioration of the steel reinforcement. So the concrete itself has a very long durability, but as far as we use with steel, we have to think about the deterioration of the steel reinforcement. So this is our history. We started the non-metallic technologies at the beginning of the 1980s. And we have three components. One, the processing tendon, another is concrete and structure. And around 2000, fiber reinforced concrete was available in the commercial base. And at the same time, we invented the butterfly web to reduce the superstructure's weight. And in 2010, the Next West is the highway company started the joint research of the Nonmetric concrete structures, and we apply the announcement, and we won because we had experience of Nonmetric, which is I'll show you some pieces of step by step. This is one first generation of Nonmetric bridge started from early 1980s. The beginning, we use aramid fiber reinforced plastic tendons. At the time, we had also the carbon, but we chose this one because the Technora by Teijin has alkali resistance. And we tried a series of tendon type, but finally we chose diameter is 7.4 millimeter deformed type because of we need some bond stress between concrete. So in the result of this R&D, we built the two types of non-metric first generation bridge in our concrete factories. And the one is a short pretension type, and another is span length is 25-meter post-tension beam. So we call this is the first generation, and this bridge is for all the vehicles. In order to anchor the AFRP tendons, we use the bond stress with non-shrink mortar. And these photos shows the temporary steel anchorage, but permanent anchorage is done by non-shrink mortar between the AFRP and the concrete itself. But unfortunately, this steel pipe anchorage is only one use, so it costs a lot. So I'll show you the post-tension beam type. We used only the AFRP tendons externally, but other reinforcement for steel, it was coated river like this. And this is the anchorage by using GFRP. And we check the reduction of the force during the time. And this is completely the non-metric bridge pretension beam type. The span length is about 12 meters. And we use the pretension tendons, FRP tendons, and also at the same time, we use AFRP reinforcement, like a steel reinforcement. So this costs a lot too. And as a result, we suspended this R&D because the cost was 2.5 times compared with the initial cost. And in 2018, we removed one of the pretension beam to check the strength. This is a result of the bending test. Compared with the design values, this about 30-year-old beam has a perfect performance compared with the design. And also we understand that we confirm that the 30 years old has the very good performance in AFRP in concrete. And after that, we rebuilt a new beam by using a zero cement concrete and AFRP. I will show you later. And we still have two pretension beam. And I told young engineers to check the behavior in 2040 to 20 years later. And also the another beams in 2090, but who knows? Okay, so I'd tell you about the new structural type butterfly wave bridge. It started from 2001. Structure behavior of butterfly wave bridge is the same as the double barrel truss. We replace the truss member to the butterfly-shaped panel. So the behavior is almost the same. We check the behavior in analysis and also the series of tests. The first application of butterfly wave bridge is in Takuboka Bridge in 2013. It's a highway bridge. The largest one is about 87.5 meter. And the basically highway bridge project, the basic design done by the consultant, and also the DT design will be done by the construction company. So this bridge, the substructure was designed by the old seismic code, and the conventional, as far as we use a conventional box girdle type, we had to strengthen the piers by the new seismic code. So we proposed the reduction of the superstructure by using butterfly wave bridge. Finally, we didn't have to reinforce the piers. So the highway company was happy. They accepted our proposal. So the panel of the butterfly were prefabricated in our concrete factories like this. So you can see the reinforcement is only the pretension steel and no reverse. And also thickness, the panel is only 15 centimeters. And also the deck, upper deck and the bottom deck is cast in situ concrete. After the Takuboka Bridge, we already built another butterfly wave bridge, including Exadol type. And also the newest one is Besodani. I will show you later. And also now another Exadol butterfly wave bridge is under construction. So we moved to the second generation of Nonmetallic bridge. We call it Dura Bridge since 2010. So in joint research with highway company, they required the cost, initial cost is 1.5 times compared with conventional bridges. And they said the maintenance cost is about 2 to 2.5 times compared with the initial cost. So 1.5 is reasonable for them. And they requires us to be minimum maintenance, which means almost no maintenance during the service. And the different situation from the first generation was we could use the fiber reinforced concrete which means we don't need to reverse any concrete. So we thought that we can meet these requirements by using these technologies. So this is a concept of the second generation of metallic bridge by using butterfly web structure and also steel fiber reinforcement and aramid fiber tendons. So as you can see, it is called the 100% non-metallic, but the highway company allowed us to use steel fiber because steel fiber reinforced concrete shear strength is higher than another fiber. So compare with the long conventional reinforcing steel, so it is no problem to use steel fiber against the deterioration of concrete. So this is material properties of high performance concrete. Compressive strength is about 80 MPa. It is not so high. And so we use 2000 Newton per square millimeter tensile steel, high strength steel, 0.5% content in volume. And this steel comes from the wire of the tires. So this is also not special material, so we can procure anywhere in the world. And we did many tests to confirm the behavior and to prepare the design manual. And one of the tests is the fatigue test of upper deck by using whale running test. This is a requirement of the highway company to use a new technology in the highway. Increase the load and up to the 500,000 cycles. And after this test, we ensured more than 100 years lifetime of the new deck structure. I show you. Very typical for the fatigue strength of the deck. It took about 3 months to get a result by using this machine. And after that, the highway company built the temporary non-metallic bridge in the present construction site. So the size of the segment is almost real size, and by using a precast segmental technologies and also all tendons aramid fiber, including external, like this. The length of the bridge is 14 meters, and also during 2 years temporary use, we collected many data to confirm the behavior of new technologies. This is in 2015. So every element of the segments were prefabricated in our concrete factories. This is the fabrication web, the fabrication of the upper deck, and this is a segment. And after the temporary trial, we built the first in the world highway non-metallic bridge in Shikoku. It's a Bestodani bridge. It completed in 2020, last year. The bridge length is about 25 meters, and also the width is about around 10 meters. So this is very typical highway bridges. And this is the prefabrication. You can see the aramid tendons, only no reinforcement. We use fiber reinforced concrete. And this is the installation of the segment at the site. We transported this segment from the factory. It's about 200 kilometers. And this is an inside view. I can see aramid tendons protected by PE stitching because of the aramid fibers. They are easily deteriorated by the ultraviolet rays. So it's easy to remove the polyethylene casing to check the inside of the aramid tendons. At the same time, we use a non-metallic concrete barrier called Dura barrier. And we use the GFRP rods because of the barrier should carry high impact force. And also in this case, we use the nylon fiber instead of steel fiber because during winter time, the highway use a lot of de-icing salt. So this barrier is the most severe parts of the highway. So that's the reason why we use nylon fiber. And at the same time, we developed the temporary plastic anchorage system called the aramid fiber. So the green one is the plastic wedge. At this moment, we use this the temporary for the pre-tensioning and the post-tensioning at the site. But in the future, we are focusing on the permanent use like this. So now it's under development by the plastic company. The wedge is almost finished, but now it's a time to develop the female cone by plastic, made by plastic. And also at this moment, we use the aramid fiber, but by using the same wedge and same female cone, we really wanted to the anchor carbon fiber and basalt fiber in the future. So this anchorage system can be used all of the fiber reinforced plastic tendons. So the next example is non-metallic bridge tech. We call Dura Bridge. The joint research started in 2019. And in this bridge, Dura tech, we use a nylon fiber, the same as Dura barrier. And then we have many old infrastructure which were constructed just before the last Tokyo Olympic game, more than 50 years ago. But now most of the highway has very severe damage because of the de-icing so during winter and also sometimes the heavy traffic. So in this case, we remove all reinforced concrete deck and to rebuild the new precise concrete bridge. In this case, we use aramid fiber longitudinally and also at the same time transversely. We use a nylon fiber 1% content in volume. So this is the first application in Tateno Bridge deck refurbishment. It's under construction now. And this is a two-span plate girder bridge. The span length is about a meter. And we remove the old reinforced concrete deck and to rebuild the non-metallic deck like this. This deck is reinforced in longitudinally, and also transversely by using aramid fiber or reinforced plastic. And also we have very small gap to join the two segments. And this is the photos of the new deck. Before the concreting, you can see the aramid transversal aramid rod, and also this is a segment. And this is the tensioning of the longitudinal aramid fibers by using a temporary rods. And this is installation of the aramid fibers into the non-metallic deck. Okay, the final example is non-metallic bridge with zero cement concrete. So we have technologies zero cement concrete and combined with non-metric technologies. Theoretically, this structure has no deterioration, and also the pH of zero cement concrete is around 11 to 12. So these technologies are suitable for the combination for the plastic fibers, plastic tendons, which means the highly durable concrete structures, because the zero cement concrete and FRP tendon can use, in the case of seawater as a mixing water, it is like a Roman concrete. So this is the characteristics of zero cement concrete. Strength of 150 MPa can be achieved without any steam curing. Dry shrinkage is extremely small, around 100 micro. And creep is small at 1/3 that of the conventional concrete. And heat generation during hardening is 30 to 40 degrees centigrade, lower than the conventional concrete, the same strength. And finally, carbon emission can be reduced up to 75% compared with conventional concrete, with the use of blast furnace slag, fly ash, and silica fuel. We check the CO2 emission. In order to check the CO2 emission, we calculate the very typical beam. This is a Ashto parvati girder. The span length is around 37 meters. This is the cross section by using conventional steel reinforcement. And the concrete volume is 18.25 cubic meter. And this is the cross section of using Nonmetallic Technologies, and 7.4 millimeter the aramid rod. And also, of course, the strength of concrete is higher, but in this case, I didn't reduction of the thickness of the concrete, though we used the same thickness, the conventional T type. This is a mixed proportion of the concrete, and the zero cement concrete. Look at this. The water bind ratio is very, very small, around 60%. Water is less than 100 kilo, and then we use a silica fume, fly ash, and then blast furnace slag. And this is a sand. Sand is very special. FNS means ferrotic slag sand. This is very basic. This has a very good characteristic to reduce the shrinkage. And normal concrete, we used around 460 kilos of cement. And in design and in zero cement concrete, we use this data. And zero cement concrete has about 120 in the long-term curing, but in this case, we have used a 28 days strength, and this is a creep coefficient around 0.2, 0.3, and the shrinkage is very small. Look at this, less than 200, and finally, we use the 100 micro. This is material properties considering design. The compressive strength is 45 in non-conventional concrete and 72 in zero cement concrete. We use 0.28, 0.56 of concrete coefficient, and dry shrinkage is 100 micro. Very, very small. And this is a result in initial CO2 emissions. In conventional concrete girder, the total CO2 emission is about 24 tons CO2. On the other hand, the zero cement concrete is 7.4. So as you can see, the concrete reduced from 6.5 to 1.84, and tendons 10.16 to the 4.8, and reinforcement 7.3 to 0.6. So in non-metric zero cement concrete, the CO2 emission from the AFRP is dominant, but totally we can reduce concrete, reduce the CO2 up to the 70% as a structure of the girder. So I calculate the through life CO2 emissions. Usually the initial cost of low carbon technologies are expensive, not cheap. But there is no research regarding relations between durability and life cycle cost. So I calculate following calculation. It is a rough cost estimation of the non-metallic zero cement concrete bridge. So as I said before, the highway companies, engineers said the maintenance cost is about double compared with the initial cost. So I use this value and say the CO2 emission are proportional to the cost. I cannot show this time because I already confirmed that this is proportional to the cost and the CO2 emission. And through life CO2 emission of the conventional girder will be 1.3 tons times 1 is initial, 2 is the maintenance, around 4 tons CO2 per cubic meter. On the other hand, the non-metric zero cement concrete girder is 0.4, or no maintenance emission. So this is a very, very rough economic evaluation of low carbon technologies. Assuming the price of carbon credit is the 150 euro per ton in the future, I didn't take into account NPV, present value, but the 150 is shown by the Norway cement industries in the future, but nobody knows which is right, but I use 150. So the CO2 emission by the conventional concrete minus the new technologies times 150 goes to the 540 euros per cubic meter. So we could think this is an acceptable price increase of low carbon concrete structures. But everything depends on the price of the carbon credit in any cases. And also we have another many parameters, but this is the one rough calculation to evaluate the lifetime of the concrete structures. So as a result, FIB has to accumulate studies to accelerate R&D for low carbon technologies. We need these studies as soon as possible. So I'll show you a little bit about the research of carbon footprint by bridge construction by Dr. Collins of UK. He showed us the capital carbon content of CO2 in each cost of the construction project. And the index added by me, and every size of the construction is about 350 to 500 ton per million euro. So I confirm the same things in a Japanese construction project. So I got the same result, around 400 to 500 ton CO2 per 100 million yen. And also these CO2s mainly come from the materials the equipment at the construction site, electricity and the fuel. So these are very, very minor, and mainly they come from the materials. So that's the reason why I focus on the materials, and also the reduction of the CO2 materials is very, very important in the future. This is concluding remarks. AFRP tendons with zero cement concrete bridges make the structure extremely durable and lead to minimum life cycle CO2, maybe the cost as sustainable solutions. The studies on the relations between durability and through life CO2 emission of low carbon technologies should be necessary as soon as possible. This leads to the right evaluation of low carbon technologies, not initial CO2 emission, but also like performance. Again, I would say the initial performance is very important, but at the same time, we have to think about true life performance of the low carbon technologies. High strength concrete can make structure lighter to reduce CO2 emission. However, large amount of cement should be necessary at the same time. Zero cement concrete can derive more than 100 MPa compressive strength and low pH. This is good for FRP use. As a result, structures which have high durability and minimum LCA can be realized as I shown in my slides. Finally, so we have to back to the Roman concrete with modern technologies. Yes, I certainly, yes. So the zero cement concrete and aramid tendons are good for the long-term durability compared with the Roman technologies. But we have some problem. So the sustainable procurement of byproducts, silica fume and fly ash and blast furnace slag. And this is one of the solutions until 2050 for the concrete sectors, I believe. And also, I didn't mention this time, the manufacturing by high durable concrete could be another key, because the long-term use, the building and the demolishing, and also rebuild again and repeat and repeat. So it contributes the reduction of the CO2 very much, because, as I said before, the material CO2 from materials is dominant up to the construction. And also after construction, to use high durable concrete is another key. So combined with the high durable structures and the manufacturing is very, very important for the concrete sectors. Thank you for your attention.